Hey guys, I just recorded a video for my latest project. The video's in two parts because I kind of talked for a long time. So just a heads up, there's a part two to this if you want to see that. So anyway, here's part one. Hey guys, I wanted to go over another project that I've been working on. This project is a accumulation of a ton of knowledge I've gained over the past year. And I've been very interested in this task, and that is how to create an effective ensemble algorithm using KNN classifiers. And so let's jump into it and see what we get. All right, so what is KNN? So KNN stands for K nearest neighbors. Basically, it's kind of the simplest classification method under the sun you could imagine. This little O in the middle is the point. This is an example image that we're trying to classify. And you can see if you look at your K nearest neighbors when K is 3, then that point in the middle would be classified as red because 2 of the 3 nearest points are red. But if you set K equal to 5, oh my gosh, then the classification for that point in the middle would be green because 3 of the 5 are green. So you can see there's kind of this majority vote thing going on, and that's how you can classify points. And so let's talk about trying to use this in an ensemble. So imagine you have 3 sub-classifiers, or 3 component classifiers in an ensemble, and their error is perfectly correlated. All 3 of the component classifiers make the same error. What do you get? You get a bad ensemble. So in this case, you can see that the ensemble's classification accuracy is 60%. That is not even better than any of the individual component classifiers. And so to make a good ensemble, what you need is component classifiers that have uncorrelated error. So you can see here that that in this situation, each of the component classifiers is still only getting 3 classifications correct. The X's stand for correct classifications, but because they're making mistakes in different places because the error is uncorrelated, they get 4 out of the 5 classification tasks correct in this example. And so we've improved from, I'll go back, 60% to 80%. And obviously this is a toy example. You know, the difference between this situation, correlated error, and uncorrelated error is just getting 1 more classification instance correct, but that's only because I have 5. When you have a lot, having component classifiers with uncorrelated error is great. You can make giant improvements. You can take let's say your baseline classifier only has 55% accuracy. If you can get a ton of component classifiers with 55% accuracy, but their errors are made in different places, you can jack up the ensemble accuracy real high, and that's what we're going for. All right, so the normal methods of ensemble learning, of bagging and boosting down here at the bottom, because they suck for this situation, they're just not good for the K nearest neighbors classifier. I'll explain why really briefly, but I want to talk about the first 3 points. So bagging doesn't work. They both don't work because the K nearest neighbors classifier is already stable, and ensemble classification thrives when your component learners are unstable, as I explained previously. So bagging doesn't work because basically with bagging, you're sampling with replacement the new training set for each component classifier. And when you do that, when I have all the training data and I'm training my first component classifier and I'm sampling with replacement and I'm getting this new training set to train my first component classifier, the probability that a data point, any given data point, occurs 1 or more times here is 63.2%. So if I have 100, an ensemble of size 100, then the probability that a given data point, or the number of expected data sets, training sets for each of these component classifiers that a given data point X would appear in is 63.2% of them. This is a problem. This is a problem because the K nearest neighbors classifier will only change classifications for a point if one of the K points closest to the point you're trying to classify is different or not present as one of the K nearest points in 50% of the component classifiers. So I'm just going to conclude really quick at what this means because I just said a lot of words and it might not have sunk in. if a point has a 63% chance of occurring, and if in an ensemble of 100 component classifiers, that point will occur in 63% of the data sets. And if you need it to occur in less than 50, then as the size of your ensemble increases, the probability that that'll happen with any point gets monotonically small. It goes down to the ground. So bagging doesn't work, okay? Boosting doesn't work for similar reason. All right, let's talk about what does work. If you use bagging and you perturb the distance metric, it works. It's been shown by, what was it? Oh man. You know what? I have a paper right here. Lest anyone think I'm not a nerd, I got hella academic papers by Zhao and Yu, who are total ballers. But they showed that if you do bagging and perturb on the distance metric, that will lead to improved performance for a KNN Ensemble. Also, your feature subsets. So if you have each component classifier trained on a different subset of features, you can get an improvement because your error will be uncorrelated. Why? Imagine you have 2 points in three-dimensional space, one here and one here. Are these points close together? No, not really. But what if you look at these 2 points with regards to, what if you drop the z-axis? Are these points close together? Yeah, they're right next to each other. So basically, depending on your, I'll throw this word out there, but like the dimensionality on what subset of features you look at, points can either be very close or not close together. And so if you have component classifiers where the feature subsets are different, then you can achieve better results. And finally, you can perturb along the k-values. So if you plot the error on the y-axis and k-value increasing from 0 to whatever on the x-axis, the general trend that you will see is that the error will be high, it'll hit a low point for some optimal k-value, and it'll go back up. But again, it could very well be the case that there are multiple k-values that give a good enough accuracy, and that with different k-values, the errors are uncorrelated. And so, this is my own innovation. We're going to explore possibly perturbing on the k-values also. If you're interested on why bagging and the distance metric work, this makes total intuitive sense to me, why when you use them in conjunction they work, but it is explained very well in Zhao and Yu's paper. And so, yeah, I'll just leave a link to that in the description. All right, so we should talk about the voting methods, because when I say voting, when anyone says voting, you're probably thinking about simple majority voting. And so each of these black boxes is a component classifier. The predictions of the component classifiers are B, B, A. The overall prediction is B. Everyone is happy. But what if, instead of only considering the prediction of each of these component classifiers, what if you returned the nearest k points for each one? So here k equals 5. So we can see the first component classifier, these are the classifications of the k nearest points, and then same thing for your second and your third. Now you have more data, so you can almost make a more informed decision when you're looking at all of the k nearest points, rather than simply for each component one throwing away everything and just returning an overall classification. And so voting with all k points, that's how I speak about it, could be very valuable. And so when you take those two options into account, you can get really fancy with your different voting techniques. You can do simple majority vote. You can do Borda counting, which is basically, imagine there is, I'll give the example of with the k nearest neighbors classifier. With Borda counting, essentially the nearest point would, for example, let's say k equals 3. The nearest point would have a vote of 3. The classification of the nearest point would have a vote of 3. The classification of the second nearest point would have a vote of 2. The classification of the third nearest point would have a vote of 1. So basically, it weights points closer to the point you're trying to classify more heavily, which makes total intuitive sense. And then you can do simple majority voting with all K, as I explained what all K means previously. You can do board accounting with all K. You can do voting where instead of just, I just described how board accounting works, but you can do things where you use the inverse of the distance metric. So that's another way of classifying points closer to, or basically, this is another way of taking points that are closest to the one you're trying to classify and giving them a higher weight, 1 over the distance metric. If you are the 5th point in a KNN classifier where K equals 5, your 1 over distance is going to be much bigger. Your weighting is going to be way smaller. So there's a lot of different ways that you can do voting, and I implemented 6 of them in this project. And, let's start looking at the results. Oh, but really quick, my data sets, I used 20 data sets for testing, and I got them from the UCI Machine Learning Repository, which is just a baller site for this sort of thing.